Let's see how much we can cover. Um, so I had left you with some questions here. So um, you have F1 and F2, both are submodular. What do you think about the max? Max of two submodular functions. Is submodular? Right, answer is there, right? It is not submodular. How would you prove this? How do you prove that max of two submodular functions won't be submodular? Sorry? Pointwise maximum won't reveal the diminishing effects. Um, yeah, but see, I said there's a relation with convexity. Minimum of convex sets need not be convex. Right? Maximum of convex sets is convex. Minimum of concave sets is convex. Is concave. And we said, well, some modular functions behave like convex functions and concave functions in some regards. Right? But here they behave neither like convex nor like concave. In fact, for max, it's not max is not submodular. And if you think min is submodular, min is also not submodular. Okay, the proof for min is given here. How do you prove? You construct. Okay, F1A is 0 for empty set. When A is 0, F2 of empty set is 0. F1 of A is 1. F2 of singleton set A is 0. F1 of singleton set B is 0. F2 of the singleton set B is 1. And finally, if you have AB, both are 1. Right? Now what happens here? F of B minus F empty. Right? Basically, the gain by adding B versus the gain in the empty set. That is 0. Now, if the original set had in addition to B as A, small a, then what happens? F of A comma B minus F of A is 1. Right? F of A by comma B minus F of sorry. Except F, I forget. The min of these two, right? The min of these two is 1. F is min of these two, right? So 1 minus 0 versus 1 minus 0 minus 0. 0 minus min of these two. Min of this is 0, min of this is 0, right? 0 minus 0. You understand? We will look at the min of each row. So you see that there's no diminishing in returns. So adding an A and suddenly the returns are higher. You understand? So this is a counter example. Proof is by contradiction. Now can you prove that max of two functions are not submodular? Can you have a similar approach? I've actually, in fact, posed more questions, but can you use a similar approach to show that max is not submodular? You'll have to construct a table like this. Do you think it's possible? Yeah, I mean, when you prove something is not, best is to show an example for which it is not. Now, it may be possible that the example is not easy to construct. Think about it for max. The other question asked here is, what if F1 minus F2 or F2 minus F1 was monotone? So if, see, we showed that min is not submodular in general. But in this case, there's a problem, right? The problem we see is F1A, 0 is 1, then you add a B, it's 0. Is it monotone? Huh? It is not monotone. Why is it not monotone? Sorry? But not So min is not monotone. You are saying min is not monotone, right? So min is not monotone because you are at 0, you are at 0, Here it's 0 and here it's 1. This is monotone. It's saying not monotone. So both F1 and F2 are monotone. Mean is F1 is monotone. F2 is not. No, F1 is monotone, right? 0, 1. B is still a single tension. So F1, F2 are both monotone. Mean of F1, F2 is monotone. But what if F1 minus F2 or F2 minus F1 was monotone? Can we put some additional condition? So let's look at F1 minus F2. Is F1 minus F2 monotone? F1 minus F2. Right? This is 0, 1, minus 1. This minus 1 will mean that it is not monotone. From 0, you have 1 to minus 1. F1 minus F2 is not monotone. Similarly, F2 minus F1 is a monotone. F2 minus F1 is also not monotone. Right? If I put a condition that both F1 minus F2 and F2 minus F1 should be monotone, can mean become monotone? You understand this? So these are. So what are the takeaways? The takeaway one. I don't want to erase this. Give you a good message. So first is prove that min and max of submodular functions are not submodular. And the second point is can min F1, F2 be shown to be submodular? Assuming F1 and F2 are under some constraints such as F1 minus F2 both F1 minus F2 and F2 minus F1 both be monotone. Okay, so you should think of some conditions which are simpler than submodularity. Right? Monotonicity is very much simpler a condition than submodularity. Just think about it. Okay, that's what if we always have F1 less than equal to F2 always, or F2 less than equal to F1 always. And so or one of them. Or not both. I mean, when you say monotone, then one will be monotonically increasing, the other will be monotonically decreasing. Okay. Right? So, however, if F1 minus F2 is monotone, then min is submodular. So that turns out to be an interesting condition. Or F2 minus F1 by symmetry. Okay. So concave over submodular, that's a very interesting class. If I have, or concave over modular to begin with. So if I have a function such as cardinality, yeah, it's actually very interesting what they wrote. So if I have a set S, and I'm trying to measure, in fact, the gradient computation on a set, which was talked about this, and a very related example. So let's take a simple example because size of set. Size of set, what kind of function is it? Is it submodular, modular, supermodular? Is a linear function concave, convex? Is everything, right? So this is cardinalities, modular, submodular, supermodular, everything. But you call it modular function. I take a function like this and I put a concave function. Square root is a concave function. Diminishing return. I take a modular function and concave is diminishing return. Okay. It turns out that these functions can be a nice class of submodular functions. Under the condition that the function sitting inside should be also monotone. It should increase. I mean, see, here we are saying, well, I put a concave function, dampen it, but the function sitting inside should not be pulling in the opposite direction. That should also be monotone, right? So it can be monotone. Inside function should be monotone. It can be submodular in general. We have just taken a modular. And the outer function must be concave. Square root is an example. So given a concave function g and a monotone submodular function f, g of f of s is submodular. It's easy to understand through modular function. So if you have a positive modular function m, so modular functions, right, if you have positive, there will be monotone. Then g of m of s is submodular. We'll see the feature phase functions, they're submodular. This does not hold, of course, if the m is negative. So if m is negative, then it doesn't hold. You will want it to be positive if it's a modular function. Then it will be monotone. You want it to be monotone. Oh, sorry. So here's example I showed on the board. The cardinality is positive modular and square root is concave. Therefore, square root of cardinality of A is submodular. We say there'll be a restricted, related stricter relation between concavity and submodularity, which will come later. As a glimpse into the connection. So there are multiple set functions, which are instantiations of either submodularity or monotone submodularity, or some of them which are just modular. So, for example, representation functions. Like the previous project presentation, what you were trying to find was I want a bunch of points which are representative. But in that process, they were missing out on diversity. Right, so diversity is another class of functions. Representation functions are facility, location, graph cut. Diversity functions are dispersion functions, determinantal point processes. They try to find very diverse set of points. Coverage functions. These are about covering features or attributes, and we'll talk about that very briefly. And there are a couple of other functions like discounted cost functions. They are interesting from a minimization perspective, not really maximization. So we will not deal with those in the class. But we have taken these examples in the motivational classes. Discounted cost function, cooperative cost, bipartite cut functions we talked about. So let's start with, so these are minimization, okay? Cooperative cost. So I want to ensure that, so what's the example of cooperative? In the case of cooperative cost, what are we looking at? So these are partitions. And I want to ensure that I pick an element, I pick a set A, such that it has good overlap or good, it is doing well with respect to each of the partitions. So A intersection Pi is a cost with, or the reward associated with Pi, right? So if I want to ensure that there is a there's a mess facility. So what will I do? And some of these messes have a common mess. Some of the hostels have a common mess. So there's cooperative cost. So I'll try to ensure that my A or set of messes are situated to represent all of these. Right now, there's a representation aspect, but if I'm trying to minimize it, then that hostel is not a good example. I want to pick an FA such that I have the smallest possible RI associated with all the AIs that I intersect with. But in this, so this it's called cooperative cost. Right? If you cooperate, the cost goes less. Right? So, or attractive potentials, another very classic example. I'm trying to minimize the energy associated with spins, the direction of spins of different electrons. So, right, if they are spinning in the same direction, then you have repulsion. So you need to you need to have opposite directions, right? So attractive. You want to minimize the energies. So this is an example where you say, okay, Eij of 1, 1. That means if I have two spins in the same direction, 1, 1, or two spins in 0, 0 directions, again same direction, then the energy. I'm sorry, this is energy is less. Okay, so this negative of energy is less than equal to Eij 1, 0 and 0, 1. So 0, 1 and 1, 0 may be more stable. Okay. So they attract each other. So that this is basically attraction. Eij 1, 0 means attraction of 1 to 0s or 0 to 1 is higher than the attraction of 0 to 0 or 1 to 1. Or complexity. If you have a large vocabulary, right, and you want to minimize the vocabulary that you extract. So imagine you have Hindi. Right? Now instead of khata, khati, khate, right, all of these variants of khana, right, I just abstract that out and have a smaller set of affixes, suffixes. Right. So you're trying to cover the vocab, but through a small. You're trying to cover the actually seen set of words through a compact vocab. So there's again a complexity. So you can have gamma of A, some square root of gamma of A. And so these are all submodular functions. These all three are submodular functions, but these are functions that you would like to minimize in general from minimization perspective. So here's an example of cooperative cost. Right? So if I have market 1, market 2, market 3, and there's a breakfast time. So what is the cost associated with shopping, the time to shop and the price of items? So where would you go? Would you go pick one item from each market? I mean, that's maybe summer break is coming and that's the best way to kill your time. You do that. But I hope you find better ways of spending your time than just go to different markets, right? So yeah, so the cost of picking something from here, the cost of picking something as fruit and bread from some other place. So there's a cost associated going to different places. The cost in time cost as well as price of item. So you would go to a place where you can buy together as many items as possible to reduce your time and reduce your overall cost because there's also discount. That's the notion of cooperative cost, right? Whereas the situation of a hostel's mess is exactly the opposite. Right? I would like to situate a mess so that it covers as many hostels as possible. You see the difference? Cooperative cost versus what I'm referring to is a facility location from. This is the cooperative cost. Okay. So if all items are procured in one or two few markets, the time to shop will be less. Additional perspective, which is not shown here, the more the number of items you manage to purchase from a single market, more is the discount possibility, which I'm not shown here, but that's another possibility. So this is some modular function. So that's another example of cooperative cost. So, but yes, it's the same idea which I showed here. I would rather pick all items from one place as far as possible because there's a cost associated with going around to different places. That's the reason we put a square root of the size. But this is submodular, but you want to minimize it. Same example I've shown here again. Non-negative sum of square root of non-negative modular functions is submodular. These are the different shops from where you're buying. What I've not shown here, as I mentioned earlier, is the fact that if I buy multiple items from one place, then the sum of those costs will be also probably less. Sorry, will be more than the actual cost of buying in bulk. That has not been shown here, but that can be an additional aspect of cooperative costs. Attractive potentials, what I was talking about earlier. But let's now take the example of segmentation, right? If I want to segment the dog to foreground and background image. So this is what I have. EIJ of 10 plus EIJ 01. Okay, so this is basically showing that there's more attraction between 10 and 01. But the other perspective is that, okay, if I pick an edge or if I pick 0 and 1 in the same area, then I'm going to have higher energy. Okay. So therefore, the way I would go about it is all the pixels I label 1 should be pixels that look similar. All the pixels I label 0 should look similar. So it's called attractive potentials. So there's attractive potentials in this. Now, in some sense, we're saying we want to minimize the energy so that 0 and 0 are attracted to each other. So it's really the complement of lower energy when you have opposite spins. You're saying you have lower energy when you have similar spins. That's why it's called attractive potentials. But the concept is same, just about flipping signs. So the first component here is modular. Ez x comma z, where x is the configuration, okay, and x is p of x comma z. Let's say is exponential of the negative of e x comma z, where basically the z is a given data image. Xi, xj are the labels you're associating with the pixels in the image. So the first component is just saying, well, what is the likelihood of xi itself? So if I'm trying to find a dog in an image, then I would expect the dog to have certain color, right? Green dogs are not seen, right? If there's a pixel in the image which is green, then it'll have high energy, because it's not going to be a dog, right? So that's the first component. That's a modular function. But second is looking at pairs of neighboring pixels and their labels, where you would expect 0, 0 to have lower energy. Is this clear? So this happens to be so under this condition, E is submodular is the spatial coherence property on the RHS. Otherwise he is not submodular. E is submodular if the E's are spatially coherent. Okay, so spatial coherence can be associated with the second. You remember we talked about two definitions of submodularity. One was diminishing returns, which was in terms of f of a union b greater than equal to minus f of a greater than equal to f of b union b minus f of b for all cases where a is a subset of b. Right? But there was another definition where instead of a subset of b, we just said f of s plus f of t, or f of a plus f of b. S, think of it as a and t as b, is greater than equal to f of s union t plus f of s intersection t. So it turns out that you can prove the submodularity in this case using the second definition, much easier. Okay. Complexity functions, the third class, which again I'm saying is we are interested in say minimizing. I gave you the example earlier, but now it's a little bit more detailed. You have on the left-hand side this vocabulary, vocabulary in the sense all the words, free-flowing words, right? And what we are trying to find is a compact set of kha, right? Which represents khana, khata. That's on the right-hand side. Selecting a limited complexity subset for quick experimental turnaround time, say. I want to learn a large language model with a compact vocabulary. So here you take A as a size or a cardinality of A, but what you do is slap a concave function on top of it to show diminishing returns, because as you keep increasing the vocabulary, obviously you're not too happy and you'd like to taper it down faster. Concave makes more sense. But there's also functions which are maximization oriented. So what so far I showed some minimization oriented functions. So coverage function, diversity function, information function, and representation function. Information functions are kind of, at the intersection of coverage and representation. But let's understand. So I'll go through each of them. The first one is sensor coverage. If I'm trying to place sensors in a room, I would place them in a way that the area that is covered by those sensors is maximized. Diversity here, let's say I'm trying to find a bunch of points here, right? Which point should I select? If I want to maximize diversity, like I want to maximize coverage here, I want to maximize diversity. How would I measure the maximization of diversity? Through volume. I'll pick a bunch of points, find the tightest bounding polyhedron for those points, and I can measure the volume of those points. In fact, that comes through determinant. So the log of the determinant is going to be representative of the volume of the tightest bounding polyhedron for the subset of points. The third is if I'm trying to select features. Okay, so find features, for example, that amongst x1, x2, x3, x4 that are best, most communicative about a class phi. Which ones will I select? So here's an example: HXA, right? Conditioned on Y, entropy of H should be maximized. Why is entropy to be maximized? Well, if the features are copies of each other, right? There's no surprise. Right? The first feature is height in inches, the second feature is height in centimeters, the third feature is height in feet. They're just copies of each other in different units. Entropy will be, what will happen to entropy? If features have copies of each other, the joint entropy will be low. Right? So that's why it's an interesting maximization problem. Or representation, right? If I have, here's blue, red, and green, to find a cluster of that is representative such that it represents all the points, right? So here you see we have picked up the one orange from here, one blue from here, one green from here as a subset of 3 points which represents all the points. They're kind of centroids, not means but centroids, right? The mean could be in a no man's land. Okay, so I'll just each of these few more minutes I'll now take some more concrete examples, and it's the last part of our class. Okay, so let's look at the first, right? The same, I'm just doing the same thing. The 4 examples I'm taking one by one. But now I'm going to give you some concrete functions. The first is representation functions. So I'm actually starting with the right hand side, the last one. Okay, so representation functions. As I said, if I'm given these sets of points, the representation would basically mean that I pick, let's say I'm allowed to pick 6, in this case 5 images, right? I could have picked this image, but I'm not. You can see, right? What have I done? I've picked 1, 2, 3. I picked this guy here. Why? Because there are too many images in this area, right? If I pick this, instead of picking this guy, if I pick this image, well, I have diversity, but I'm not representing a majority of the images in this region, right? So this is a representation, which is probably like the spirit of the paper you presented. right? More representation. So let's look at examples. Oh, here's an right, facility location is a very classic example. What am I trying to do here? Okay, so I have kind of annotated it. I'll go back and forth. So let's look at this SIK, this pink, right? Is a you want a bunch of pink edges. People are there in different towns. Okay, you have people, clusters of people in different towns or villages or wherever. And sorry. And what am I doing? I'm basically I'm trying to find for each set of points, right? Which is the closest facility. So this pink, this blue is a cluster representative, right? I'm trying to find a bunch of X. The K is basically ranging over all the blues. Pick a facility in blue which is closest to my location or my village, which is in gray. So max over K in X of SIK. SIK is a similarity function. How similar or how close is I to K? This is I, this is K. Okay? And then for each I find the most similar K and then sum over all the I's. Right? So for all the locations, I'll find. So I want a bunch of X's which are most similar, or the K in X, which are very representative of as many of the villages or people in the villages as possible. That's facility location. So this sum over max of SIK is submodular. By which property? Well, is max? No, max was not submodular, right? So none of the properties we have studied so far will directly, well, for sum is okay. If you can show that max of SIK is submodular, then sum is fine. Okay, so this requires little work. I'm not going to prove, but in my earlier courses, I would actually spend a lot of time proving. Very nice proofs. Okay, let's look at the second one, saturated coverage. Okay, the only difference, so I have the same SIK here also, right? But instead of a max over K in X, instead of finding the most similar guy, what am I doing here in yellow? You're saying every point in ground set V is voting. There's a V voting for every point in the subset X. That's what this is doing. Summation over J in X, Sij. Every point I in the ground set is voting for every point J in X. But like elections are around, right? So everyone votes. But then what are we saying? Oh, but there's a threshold up to a limit alpha I, right? So I can vote, but I cannot cast more than one vote. In this case, you can say, well, there can be might be more than one or two votes. People can vote multiple times, but up to a limit alpha I. So this, so then you look at min. That's why looking at min to threshold. So this is a submodular function, but it is unlike the coverage. It's saturated coverage. So it is a representation function and not really coverage function. The third example is graph cut. So graph cut is kind of the combination of these two, previous two. What are we doing here? We're saying, well, what is the self similarity between all elements of X and all elements of V? And then from that, you subtract out self similarity. Okay, similarity of every point I in every point, every point ij in X. Subtract that out. So self similarity remove from the overall cross similarity. But there's a lambda, right? You're not just subtracting. Otherwise, we'll say, okay, all the self similarity is gone. But there's a lambda, and the lambda governs whether it is submodular or not. Okay. So, so it turns out that if lambda is less than 2, If lambda is equal to 2, it is monotone submodular. If lambda is less than 2, it is not monotone, it's submodular, but it's not monotone. Okay. All the others, these two are monotone submodular. Okay. You're getting a flavor, right, of these functions. So what is the third one doing? Subtracting some weighted self similarity of points in X from cross similarity between X and Y. But that's basically saying, okay, discourage self similarity reflected through the diagonal dominance. Sij, the similarity matrix will have some diagonal elements of self similarity. It's saying, okay, diagonally dominant component you just remove, but not remove blindly, but remove with some discount. That's the lambda. And the texture explanation, points in X should represent points in V minus X more than they represent themselves. That's all. Okay. So this is a summary of the representation function. I think pretty much everything I said. So you can try and prove that this is submodular. Oh, okay. I'm just going to skip it. But diversity functions, let's cover these function classes. Now, diversity functions are actually, in some sense, easier to understand. There are not too many of these. So here you're looking at trying to pick a bunch of points which cover diversity in the space, right? Not just set of points. So therefore, volume becomes interesting. You're not just covering other points, but you're trying to maximize the spread in the space, right? So therefore, volume is natural, and log det of the submatrix of this cell. L is basically a matrix of similarities. You take a submatrix LS of that, and the log determinant of that is a volume. So the idea is pick the items as different as possible. So you can see in this case, I have picked my loner here. It's an outlier. Exactly what you're saying. So outlier, unfortunately, outliers here will be picked up. That's why I was commenting in the presentation that what is an outlier? When is outlier more desirable? When is diversity desirable? Beyond the point, unless your validation data, it's very difficult to ascertain. So validation data will say that this is a class having 5 examples to be discarded, or is that a class of real interest? Right? So that's how hot can you look for? Might be very rare. But if you're looking at PET-CT scans, you're not going to say, well, these are outliers. So those are the ones you want to target. So these recipes are there, but to use them wisely, it's often good to be grounded in the data. These also give you the facility to be grounded in data. The only challenge is log det is submodular, but somebody there. Somebody from CSK office. Okay, no problem. So log det function is on submodular but not monotone. The idea is pick items as different as possible. So this is the detailing of that. You have a similarity matrix with Lij is Xij transpose Xj. And let's say I have a sample set Y. You look at the determinant of the submatrix LS. And that determinant is basically going to be the volume of all the points Xi in the space that you select, from the subset that you select. So if you use, say, DPP for sampling a bunch of points or finding a subset of points, you'll find that much better spread than uniform. So it's not just there's volume at every level, volume even within the subset of points within that. Right? In every region, you want the volume to be maximized. That's what it's doing. Unlike uniform, you'll suddenly have lots of points here and then no points here. You won't have that in DPP. So basically, If you have logged it and then you have a suitable normalization, then it becomes a distribution. So that's why it's called determinant and point process, right? There are other diversity functions as well. So for example, you can look at distance Dij between elements I and j instead of similarity. Earlier we were looking at similarity. And what will you do? Pick items as different as possible. Okay, so dispersion means sum. What will you do? You'll pick for every point in the subset that I want to select. I look at how much is the distance of that point from any other point in the same subset. You see a big difference here. Our facility location, the outer summation was what? Was over what? Was it over X or over V? Over the subset or over the entire set? This outer summation. It was over the entire set. Here, the outer summation is also over the subset that you want to select. And the inner minimum is also over the subset only. So basically, I'm saying that, oh, I'll pick a set such that the points within the set are as far away as possible. I don't care for the overall set because I don't care for representation. That's the whole idea of diversity. Diversity should be only a function of what I pick and not what I don't pick. Right? So this is submodular. Now you instead of saying sum and then min, right? This is min distance for each point x, each point k, the minimum L. But instead of that, you can say, well, I want the min over all and all the k's and all the n's. Right? No summation. This is not a submodular function. Unfortunately. If you take a min over all of them, you need a sum and min, that is fine. Or dispersion sum. Okay. Dispersion sum just saying, okay, take all pairs of points, find their pairwise distances, sum them up. This is not submodular. What is it? It is modular. So you say it's not submodular in the sense, right? It is simple modular function. Right. So this is what they'll drop all these outliers and pick a bunch of points in the main set. So this is kind of similar to DPP. So all of these in one place. Dispersion sum is not is modular. Dispersion min sum. No, there were some papers, right? So dispersion min sum is submodular as per a subsequent paper. Okay, so some 2015. There was an original paper where they said it isn't, but then there's a follow-up paper. Right? So it is. So there's a bug, right? It is not submodular. Okay. And the final set of class of functions is coverage functions. Coverage is again very simple, right? I think the representation functions are not trickiest. These are simple functions. So if I have words cat, dog, bird, man, beach, right? So what am I trying to do? I'm trying to pick a bunch of documents which cover as many of these words as possible. So give me a document which has all the words rest. That's coverage, highest coverage. But if one document may not contain all the words. So here, what have I done? Well, these edges you can see. So I basically picked up these two documents because they the black edges they cover all the words, right? So select instances which cover all concepts. That's the whole idea. Now you may also associate a weight with the coverage. So W outside, what is X? X is a set of documents I cover, documents I'm using to cover. So I is in X means it's a single document. And looking at all the union of all the words covered by all the documents. And then you can add a weight which says, okay, for each word that is covered, this is the weightage. So you can have a weighted feature coverage. Here's an example on the right hand side. So let's say these are the features: male, car, greenery, beach, water, mall, female, and so on. So I'm trying to pick a subset of images which cover as many of these features. See the difference between representation function and coverage. Representation, I was trying to represent one image using another image. In coverage, I'm trying to cover features and not images. So there's no similarity function. It's a discrete element I'm covering. Okay. As a last question, you may ask, okay, what if these are not discrete? What if I have probabilities? What if I have a detector which says, oh, this is male with a probability something, something. I can't find a gender deterministically. So how would you change this function? Any suggestions to make it probabilistic? Here's the last question. Softmax, okay. The softmax, you'll still, threshold, right? Okay, so this is work we did long back, right? We wanted to cover. This is a Wikipedia graph, and we were trying to pick a bunch of topics which cover as many of the articles as possible. And this is a paper we had where we were trying to learn learn to generate Wikipedia disambiguation pages. Word like Apple. You like to ensure that Apple can be a band, Apple can be cashew apple can be an album. So many meanings of Apple here, right? Which meaning of Apple should I pick? How do I cluster? So instead of treating all the apples as different apples, you can say, well, 2-3 apples look very similar, right? The Apple Inc., Apple Bank, these are all organizations. The Apple is, I think it's the album, right? Or possibly the album. Cashew apple, and Apple Store. Some of the other apples are really about the fruit apple or associated eatables. So I can create these smaller partitions. So the problem there was basically, so here's it, right? On the right hand side, you see the grouping. Technology, there are a bunch of apples. Companies, a bunch of apples. Music, a bunch of apples. Right? Plant, a bunch of apples. Right? So this is coverage. Pick a bunch of higher level nodes which cover as many of the leaf level nodes as possible. But as I said, you can have a probability associated. Here you see, if I pick these two, I only cover these four leaf level nodes. But if I pick this one and this one, I've covered the entire bunch of leaf level nodes. Right? So there's, I'm not going to get into the details of how the set cover is submodular, but answer to the question, if I had a probability, what will I do? I have a Pij. Pij, that is the probability that image I covers concept J. So I have a product over all the i's of the probability that none of the, yes, what is it? None of the, it's a product over I. None of the so 1 minus Pij is a probability none of the images cover that concept J, right? And now 1 minus this product, what does it mean? 1 minus the product. At least one image covers that concept J, right? With the weight of that concept. Sum over all the concepts. You understand? So this is the nice probabilistic variant, and this is also a submodular function. Same idea. Okay, so I think we have given you a flavor of these submodular functions, and they're very interesting. The optimizations for algorithms for these submodular functions are very simple, nice, greedy algorithms. So from an application perspective, this is good enough, right? Just understanding what are these submodular functions in practice, how can they be used is good enough. If you need more details on algorithms, you can refer to my previous year's recordings. But I think this is good enough for this course, especially if you're embarking on some course projects. Any questions or comments before I wind up. Okay, so